Hello and welcome. This is Chapter 1, Section 5, Part B of parent functions and their transformations. Our goals today are understanding reflections over x and y axis, as well as vertical and horizontal transformations, and interpret the graph, each segment of a piecewise defined function, considering its rules and domain restrictions. So reflections, we can reflect over the x or the y axis. It's going to reflect across either what we're going to do the x-axis, which how you do that is we're going to change the function y equals to the opposite of that. So we're going to just switch all of the signs from positive to negative or from negative to positive of that function. Now a reflection over the y-axis is if I substitute in negative x, and that will flip everything over the y-axis. So what we're going to do is graph this function y equals negative f of x. Given that this is my regular f of x, we're going to flip it over what the x-axis is. If you remember from the last page, that's the x-axis. But what we can do is it just says change the y value. So if this y value is positive 1, well, we're going to match that with a negative 1 down here. So that is my new point there. So if I go to this y value right here, again, we can use our pencil tool to write these. So if I have that as my y value, which is at 4, we are going to go to negative 4 in that same x location. So the x will remain the same, but the y values will be the opposite of each other. And then that last point here, we're going to a positive 5. That will match a negative 5 right here at that same value here. Now I'm going to erase this so it's out of my way, and we just have to connect those with this line tool. So this line tool, you connect that to that and that to that, and this should be a perfect reflection over the x-axis. Now another example 1 part B in this case, which we're going to reflect over the y-axis this time. So remember, this will say the y-axis if we plug it in. So we're changing the x value from positive to negative, so my y value stays the same here. And we're going to move it over, well, the x value was 2, so I go to negative 2, the opposite of it, and keep the y value the same. So the y is still 4, but I just switch around my x values. Now there's only one other end point here that I'm going to focus on, which is right here, which again is at 6. And we want the opposite of that for the x value, which is all the way over here at negative 6. We do not want this here, but we just wanted to show you how you move over there. Now again, we use this pencil tool to draw the dots, but then we're going to click the line tool to connect the dots. So this is a perfect reflection over the y-axis, or looks like it's pretty close, because I can't draw straight. So this leads into another type of transformation, which is called a dilation of a parent graph. This involves either the stretching or the compressing, or what we can say is the shrinking. So I like to say compressing is shrinking of a graph, either vertically or horizontally. These transformations affect the width or the height of the graph without actually shifting it. So we're not actually going to shift it left or right. Think about your eyes. If you dilate your eyes, if you go to the doctor, your eye pupils get extremely big. So it's expanding that or stretching that out. So let's talk about the dilation. So a vertical dilation, a stretching or compression, affects the y coordinates of the graph. So vertically, think up and down, which is your y coordinates. So what we're going to do is we're going to just multiply outside. So the first thing to notice is that this is outside of the function f of x. So we're just taking and multiplying the whole function by some number. That number will tell us what's going to happen. So if this number here is a value that is large, like 7 or negative 7, we'll say the value of it, so how close it is or far away from 0 it is. So we're going to put absolute value. So if this is a 7 or negative 7, that is bigger than 1. If it's bigger than 1, it's actually going to vertically make this taller, stretches it out vertically. So it shoots up extremely fast. Now a compression, like if I want to multiply the function by 1/2, if I multiply by 1/2, it will make something smaller. So it will make it shorter and will compress it or push it towards the x-axis. So let's jump to Desmos just to show you this. So bringing up Desmos here. So if we think about this, let's just put it in the middle here. Let me move that out of there. Sorry. There we go. So we have a square root function here. So let's say we have the square root of x. Let me get my tool. This is this graph. That's how a square looks. If I multiply by 1/2, it should shrink or shorten this, making this closer. So if I take any of these values, like this value here is at 1, it should be half of that if I multiply by half. So let me go back into Desmos here. Let me click, click, click. There we go. So if you look at that, it does in fact shorten it, and it is half of that function. So as we go along this red graph, if I multiply any of these y values by 1/2, that is half of the height of that. So blue is half of whatever the red is. Now if I think about 2 as doubling, it should be double the height, so it should be up here, twice as big. So, and it will get further and further apart as I go further and further to the right. So let's go into the graph. Come on, let's go into the graph. There we go. So, and as you can see, that will double that value. Now let's look at horizontal dilation. So that is the stretching and compression of the function. So, but in a horizontal direction, so left and right. So this is going to be happening if I substitute something into the function like b. So if it was like 3x, I plug into the function. So or 1/3 x, I plug into the function, and that will do it for all of the different x values I substituted into. So we have to think inside for horizontal dilation. Now, if by chance it was 0 to 1, like 1/3 or -1/3, it's actually going to stretch the function, and we're going to stretch it horizontally, so making it wider. So it stretches it horizontally. So this is kind of the opposite of each other, but it will look identical on a graph of what's happening, and I'll show you that as well. So a compression is if I plug in like a 3 or a -3 here into this function, so it's like 3x or -3x, it will actually horizontally make it narrow, so it will actually shoot the graph up faster at the y value, but it will make the x value narrower. So let's look at some Desmos. So looking at this on Desmos here, we have our original y equals square root of x. So if I plug in 1/2, what's going to happen is it's going to stretch horizontally, making it wider. So it's going to actually shift it faster to the right versus going slower to the right. So if I do that, let me click this. So as you see, it's very similar to plugging 1/2 outside of the function, but we're going to think of it as a dilation where it shrinks left to right here. So it kind of pushes it out faster to the right horizontally. So it's flattening out faster or going to the right faster than this was here. Now the other one is going to go slower to the right, so it's just going to kind of slowly, lazy go up here. So we're not thinking about vertically at all, we're just thinking about left and right. So if I click this again, this will actually compress because it's a value that is bigger than 1. And like I said, it's just going to move slower to the right. Your y value goes up slower, and that's what's happening here. And it's hard to think about it when you look at the graph. But the main thing is, well, you have to look at the values here, and that's the only way to really determine in which type of dilation it is, if it's inside or outside of the function, and what is the value that's being multiplied. So a couple examples here. So our first one is, notice how it's outside. So it's going to take this y value and times it by 2 or double it. So this means to double the y values. That's what it's saying. So we're going to look at these values. I'm just going to go to the endpoints, and we're going to double whatever those values are. So the x value doesn't change, but the y value does. So if we look here at -2, if I double that, that is going to go to -4. So at this point, it will be -4. And again, just to clarify that, so whatever this value is, we're going to times it by 2 to get to here. Now we're going to go to here, which was -4, and we're going to times it by 2 to get to -8. So -4 times -2 is at -8. And then we just connect the dots again with our line tool as best we can. So just like that. So this value is double that, this value is double that. And we're talking about the y values because it's outside of the function. Now, when it's inside the function, this will double, because it's times by 2, this will double the x values, and the y values will remain the same in this case. So we're going to look at these values here, these corner points, and we're going to double each of the x values. So if we're looking here, what is the x value of this? Well, -2. We're going to times -2 times whatever that number was, which -2 times 2 is -4. So this new point goes to -4. Remember, the y value is not changing. It's the x value. So we're doubling the x values because it's in the function. We're doing that horizontal dilation. So now we have that new point. Now my x value is 0 here, and I'm going to double 0, and it still remains 0. And then I look at this one, the x value is 4. I'm going to double 4. 4 times 2 gives me this 8. Again, the y value remains the same. The x value is what changes. Now we just connect those dots, and this is my horizontal dilation.